many times in chemistry, we'll see different molecules that have the same constituent atoms. For example, these two molecules here, they both have 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4. So if I were to write their chemical formula, it would be C4, and then they both have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So both of them have the chemical formula C4H10, C4H10, but they're still fundamentally different molecules. And you can see that because they have different bonding. For example, over here we have a carbon that is bonded to 3 other carbons and a hydrogen. Over here, I can't find any carbon that's bonded to 3 other carbons. I can find ones that are bonded to 2 other carbons, but not one that's bonded to 3 other carbons. So how we've put the atoms together is actually different. They're bonded to different things. And so when we have the situation where you have the same constituent atoms, where you have the same chemical formula, but you're still dealing with different molecules because of either how their bonds are made or what their shape is, we call those isomers. So an isomer, you have the same chemical formula, but you could have different bonding, but different bonding or shape, or orientation. So over here you have just different bonding, and this type of isomer is called a structural isomer. So these characters are structural isomers, same constituent atoms but different bonding. Structural isomers. So that's structural isomers right over there. Now when you look at this pair, you say, well, hey, those don't look like structural isomers. Not only do they have the same constituents, both of these, for example, have 4 carbons, and they both have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, and they both have 8 hydrogens. So we could these are both C4H8, H8. It looks like they're bonded similarly. For example, I mean the left-hand side here, these look identical, and on the right-hand side, you have a carbon bonded to another carbon that's bonded to 3 hydrogens, carbon bonded to another carbon that's bonded to 3 hydrogens, carbon bonded to a hydrogen, carbon bonded to a hydrogen. So it looks like the bonding, everything's bonded to the same things, but you might notice a difference. Over here on the right-hand side, this CH3 is on the bottom right, while over here it's on the top right. And you might say, okay, well, what's the big deal there? These, all these molecules, they're all moving around. Maybe they're rotating with respect to each other. And this thing could have rotated down to become what we have up here if this was a single bond. A single bond would allow for that type of rotation. It would allow for these things to rotate around each other, for the molecule to rotate around that bond. But a double bond does not allow that rotation. So this fixes these two things. This fixes these two things in place. And because of that, these are actually 2 different molecules. Over here on the top, you have the CH3 groups. They're both, I guess you could say, facing down, or they're both on the same side of the double bond. While over here, they are on different sides. They are on different sides of the double bond. And so this type of isomerism, where you have the same constituents and you even have the same bonding, this is called stereoisomerism. So we're caring much more about how things sit in 3 dimensions. We don't just care about what's bonded to what or the constituents. And actually this one, as we'll see, this is also stereoisomer because this carbon is bonded to the same things in either case. So these are both situations. These are both stereoisomers. Stereoisomers. And this particular variation of stereoisomer is called a cis-trans isomer. Cis is when you have the 2 groups on the same side, cis, and trans is when you have the 2 groups on the opposite sides of the double bonds. Cis-trans isomers. Cis-trans isomers. And these are often called geometric isomers. Geometric isomers. So that's a subset. So when I'm talking about cis, trans, or geometric, I'm talking about these two characters over here. They are a subset of stereoisomers. Now what's going on over here? I have no double bond. I'm not talking about cis and trans. The carbon, as I just said, is bonded to fluorine, chlorine, bromine, and a hydrogen. Fluorine, bromine, chlorine, and hydrogen. How are these two things different? And the way that they're different is if you were to actually try to superimpose them on each other. You will see that it is impossible. They are mirror images of each other, and because there's 4 different constituents here, you cannot superimpose this molecule onto this molecule over here. And actually, because of that, they actually have different chemical properties. And so this over here, these two characters, which is a subset of stereoisomers. Stereoisomers are concerned with how things are positioned in 3 dimensions, not just how their bonding is different. But this subset, where you have these mirror images that cannot be superimposed, we call these enantiomers. So these two characters, these are enantiomers. Enantiomers. And enantio comes from Greek, the Greek word or the Greek root opposite. So these are opposites of each other, and they cannot be superimposed. They're mirror images. So all of these are different variations of isomers. And once again, you might say, okay, these are clearly 2 different molecules. I have different bonding. But even cis-trans isomers will have different chemical properties. These 2 in particular, they aren't that different, but they do have different chemical properties. But sometimes they're so different that one might be able to exist in a biological system while the other is not. One might be okay for your health and the other might not be okay for your health. Same thing for enantiomers. One might be biologically active in a certain way and the other one might not be biologically active in that same way.